Welcome to the second training video for the Harmony MS. In the first video, you must have heard about the main goal behind building a Harmony MS. In this video, we will talk about the main concepts and recap also the main concepts from the first video, and also give some more technical details about the architecture of the model suite. So here's our presentation outline. First, we start with the concepts and terminology. So there are four main concepts in the Harmony model suite: modeling components, modeling templates, projects, and scenarios. We will look at them one by one. Modeling components. Essentially, a modeling component represents the basic executable unit of the model suite of our platform. And it corresponds to either a simulator, for example, AIMSA Next, or an open source simulator such as Sumo, or another piece of software that in transportation is typically called a model that we can execute via the platform. For example, we will see several examples. One of them is the land use transport interaction model. What's important for the platform, for the Harmony MS, is that each modeling component needs to have a well-defined set of inputs and outputs. This can be, for example, inputs can be files with data that the component needs, or some configuration options. For example, some integers or some strings that are needed for the component to run. Also, what's important to note is that with each component we associate in the platform a set of key performance indicators that we will use later on to evaluate the run of the component. The second main concept in our platform is that of a modeling template. A modeling template contains one or more components that should be run in a sequence. So, in a sense, it is a combined modeling component. So essentially every model, and we will see several of those, is a modeling component for the MS. And when we combine modeling components, which is something that one of the main functionalities of the MS is the combination of those components, we create a modeling template. For example, a template at a strategic level can be a combination of DFM, light component, REM, and LUTI component. Now, the third main concept of the MS is that of a project. So a project is created via choosing one of the modeling templates from a list that the MS provides, and instantiating this modeling template via providing all the necessary inputs to all the components that belong to this template. A project, once instantiated, contains already a default scenario that you can already run, but in general a concept can contain as many as possible scenarios. One of them is always the default scenario, and you can have several alternative scenarios. Scenario is also the fourth main concept of the MS, which basically represents the basic unit of analysis. And it corresponds to a single run of all the components that belong to the template that you instantiate when you create a project. Also, the difference between a default scenario and an alternative scenario is important to understand. So basically, an alternative scenario is a scenario that is created from the same template as the default scenario, and also belongs to the same project as the default scenario, but it has changes. It is different from the default scenario in one or more of values of its inputs. So, for instance, if you want to compare a transportation policy in a city, you will create you will assemble the components that you need for this analysis. then you will create a project, by instantiating a template and adding all the necessary inputs to this particular template. For instance, you might want to add the radius around the center of the city where the analysis should focus on, and this can be one of the parameters that you choose when instantiating a template and creating a project and default scenario. Then an alternative scenario might be, for instance, changing this radius into a bigger value or a smaller value, and creating another run of the same thing. So that would be essentially an alternative scenario that you can compare to your default scenario to see which radius brings different. How changing the radius changes the result that you see in the analysis. Okay, so in other words, once you create a template, for instance, you can create a template for a Turing project. Once you create a template, you can upload the input files representing the metropolitan area to initialize the related project. For example, you can do that in the case of a city, such as Turing was one of the use cases in the Harmony project. But you can use the same template to create another project that has all the necessary files for the Athens case or for the Oxfordshire case. This will correspond to different projects. Now, having the different projects, for each project, as I said already, a default scenario is automatically generated. And then you can have several. Here we see, for example, 2 alternative scenarios to the default scenario. By basically changing some of the inputs to this particular template used in the project expects. So, for instance, you can here increase the GDP and see what this means for this particular scenario, and also comparing the results of the high GDP to the other 2 scenarios. So, putting it all together, in the MS, you will have several modeling components. Here we see 3 of them, and you can combine them in different ways. For instance, you can combine all 3 modeling components. All of those belong also to the strategic level. We will see later, into templates. Here we combine all 3 of them into a single template that first runs the DFM model, then runs a regional economy model or REM model, and finally runs the LUTI model. And once you do that, you have a modeling template, and then you can instantiate it, as we saw, in different cases by providing different input data. For example, if you provide input data, supply and demand data, for instance, regarding Turing, you would create a project, a Turing project of this particular template. If you provide data for Athens, you would create the Athenian project for this particular template. If you provide for Oxfordshire, you would create a Oxfordshire project using the same template. And then for each project, you can create different runs, which we call scenarios, and compare different interventions in the same overall case. This is also shown here, where, for instance, also shows the evolvability of our platform, because our idea is that also in the future we will have more components that can be used with components that are already in the platform. For instance, here we have the activity-based model, a tactical level model that is provided to the platform and offers also the possibility of being combined with the REM and the DFM into another template, which again is instantiated into projects. And those projects, for each of those projects, we can consider several, one default and several alternative scenarios. Note that there are one of the also important concepts for the platform is that of the user role. And we distinguish two main user roles in the Harmony MS, that of the modeler and that of the planner. So the modeler essentially is responsible for creating modeling components and assembling modeling templates out of those modeling components. The planner is then responsible for taking those modeling templates, even if the planner does not know what exactly the implementation choices are in those templates, and instantiating them. The planner really has this more end user's perspective on the platform. Of course, the modeler can act as a planner. The same person can play both of those roles, but in general, we have these two distinct roles in the MS. Finally, one important last main concept is the Harmony dashboard. And essentially, the dashboard is an application that is integrated with the main Harmony model suite and is used to visualize results from the different runs, or as we call them, the different scenarios. The visualization is done in terms of KPIs, key performance indicators, and the visualization takes different forms. For instance, you might have a KPI which shows a graph or shows a map, like here in the slide, or maybe a table with results from a single run. What is also important to keep in mind is that the dashboard of the MS offers the possibility of comparing results, comparing scenarios that belong to the same project by looking at the results side by side. So this is useful for transportation analysis and decision making. Okay, so this is the first part of this presentation. We talked about the concepts and the overall terms used in the platform. And now I would like to give you an idea about the overall architecture of the model suite. This part is a bit more technical, so let's jump into it. So you might be asking technically what is really the Harmony model suite by now. So essentially the technical answer is that it is a really web application. So an application that you can access via, for example, your web browser, which is built with modern technologies, to mention a few, Angular, Python for the backend, and Kafka for the communication. We have built it following three main guiding principles. First, we wanted the platform to be software agnostic, which means that the transportation models should be able to be written in any programming language. So transportation models correspond to a modeling component, as introduced in the previous slides. Second, we wanted the platform to be open and extensible, which means that the transportation models should be easy to integrate. We wanted also to make sure that we provide an integration process for new components even outside the length of the Harmony project to be integrated possibly in our platform. And third guiding principle is that of ease of use. So we wanted to make sure that the end users that we target, which are basically transportation planners and decision makers, would be able to run relatively complex analysis, but in a straightforward way, by really clicking some buttons, and also visualizing the results again in an intuitive way, again by selecting some KPIs and clicking some buttons to create their own view over the dashboard. So these are the three guiding principles of the Harmony model suite, or the Harmony platform, if you prefer. So now I'm gonna try to explain how we try to fulfill those principles via the different choices, technical choices mainly, that we have done. So first, some words about the overall architecture of the platform. I have already mentioned the two roles, transport modeler and transport planner. Here we also see in the slide these roles, but also two more roles, so that of the maintainer and the component developer. The maintainer is the role of the person or the people or the team that actually deploys the platform and creates, for example, new users and user roles, etc. Component developer is a role, again, a technical role of the person or the team that actually develops the software, the new components, the new modeling components to be integrated into the platform, and with the help of the maintainers, they integrate the new components in the platform, and these components are available to transport modelers to create templates with. The platform itself is a three-tier application. So we have the presentation tier, which is, if you want, in other terms, the front end, the application tier and the data tier. The application tier and the data tier are the backend of the platform. In terms of technical decisions and technologies used for the application front end, for the user interface, we have used the Angular framework. It's a TypeScript framework for the creation of the dashboard, which is a different application but integrated with the Angular application. We have used a low-code visualization framework called DAS, where basically the visualizations are written in Python, and then JavaScript code is generated out of this. For the application tier, which consists of the logic that basically takes the user's request from the front end and runs the different components in the right sequence, and also generates the results, also saves the results in the database. We have used Python, and in particular a framework called Flask, a REST framework for creating web applications called Flask. For the provided modeling components, we have not prescribed an implementation language, so we wanted to be language agnostic. So here really those can be written in any implementation language, and I will explain in a few minutes how we achieve this. And of course, finally, for the database, we have used a document-oriented database called MongoDB. Finally, for a few words also about the communication. So the front end and the back end, presentation tier and the application tier, if you want, they communicate via HTTP, and the other parts of our application communicate either via Mongo, which is MongoDB, which is basically the protocol that you connect to the MongoDB database, or the file system API to basically read from the file system on the server side, or via Kafka, which I will describe in a bit more detail again in the next slide or slides. Also now, if you look at the architecture from the perspective of deployment, you basically will see that we have made the choice of the conscious choice of structuring the application from the deployment perspective as a microservice architecture, and we have used container orchestration technologies. In particular, we have used Docker containers. This allows us to have loose coupling between the components of our application, and also allows us to have those provided modeling components written in any programming language. Essentially, a Docker container, you can think of it as a lightweight virtual machine. So our database, the dashboard, as you can see here, all of those rectangles correspond to individual Docker components in our deployment architecture, and each of the provided components also is packaged together in a Docker container. So this way, if we want to integrate a new component to the platform, we have to make sure that we wrap it into a Docker container, and then we'll be able to run it alongside the other components without big problems. So on the integration of the component, let me give you an example just to have a better idea of the different steps that are involved here. Let's assume that we have the code of a component that we want to integrate. This, for instance, is the tactical freight simulator component that was developed and enhanced during the Harmony project. Once we have this, the code, the first step is to add the code in a Docker container. This is done to be able to execute it from within our modeling suite, and also it's mentioned also on the slide for cross-platform execution. This means that by wrapping it in a Docker container, we can run it. We include all the dependencies of this code, and also we are able to run it in different environments, for example, Windows, Linux, or Mac machines. So that's the first step. The second step is making sure that we have a well-defined interface. This means that we need to specify clearly, and we're using a well-defined language, what are the inputs and the output interfaces for this component. In other words, what it expects when you use this component and want to run this component, what files or other inputs it expects, and what it provides, what it generates. Most of the times, the components generate some files that contain data that are used in the visualization of the KPIs. So how does this look like? The input and output interface, it might look like something like that. Basically, we have, this is language called protocol buffers that we have used here. And as you can see, a component might have several inputs, some of them also of different types. So some might be strings, or files, or integers, or floats. And similarly, a component might have several outputs. So we need to specify those inputs and outputs, and so that we are able to, using this specification, to compose components together into templates. If we don't have such a specification, then this composition cannot be done. So that's a necessary step, number 2. The third step is the actual integration process. So basically, where we update, and this has several sub-steps that I will not go into, but we need essentially to update some small pieces of the Harmony MS code base of the server side to make sure that we are able to communicate with this component, and we're able to, for example, start the execution of this component and receive the results after the execution. Also the progress, because each component actually sends to the platform periodically progress and execution messages about its execution progress, so the user can actually see in the interface how long more to wait, for instance, for the component to finish its execution. Okay, so just to give you also an overview of the components of the MS that are implemented and integrated within the Harmony project, and you will hear a lot more about probably each of those components in subsequent videos. So at the strategic level, we have 3 levels: strategic, tactical, and operational. At the strategic level, we have several models, and here we can list 5 of them. At the tactical level, we have the tactical freight simulator and the activity-based model. Operational, we have the operational freight simulator, the operational passenger simulator, and the energy and emissions model. And again, these components can be run as they are, so basically alone. So you can really create a template where you only run the TFS component, right, without any other component. But really the main idea of the Harmony MS is to integrate components together. And again, that we achieve by creating modeling templates. For instance, what you will also see in subsequent video is a modeling template that integrates the DFM with the regional economy model and the looting model in one mega model, if you want. And another template that you will see is one that integrates the strategic freight simulator with the tactical freight simulator. So in a sequence. So first the strategic freight simulator runs and then produces some outputs that are used by the tactical freight simulator. Okay, so this is all for now, for this video. I hope now you have an idea of the main concepts of the MS and also some technical decisions that were taken about the architecture and the integration of the code in the MS platform. So thank you very much. And here is my name and contact details.